Alright, let's go. Number 10. The missing magnetic monopole. Paul Dirac in 1931 was not looking to break physics. He was trying to explain why electric charge comes only in discrete units, why every electron carries exactly the same charge, never a fraction of it. This was, at the time, a strange coincidence nobody could justify. Dirac was doing bookkeeping, tidying up quantum theory. Maxwell's four equations, written down in the 1860s, describe every electromagnetic phenomenon in the observable universe. Radio, light, radar, the microwave heating your food. But the equations are structurally lopsided. Electric charges exist as isolated positives and negatives. Magnetic charges, isolated norths and souths, do not appear. The symmetry physicists find beautiful and every other law is missing here. Dirac showed that if even one magnetic monopole existed anywhere in the universe, quantum mechanics would force every electric charge to be quantized in exactly the pattern we already observe. The paper was titled Quantist Singularities in the Electromagnetic Field, published in the Proceedings of the Royal Society A, Volume 133, in 1931. Decades later, on February 14, 1982, physicist Blas Cabrera at Stanford recorded a single, textbook perfect monopole signal in a superconducting loop. Valentine's Day. One event. Every subsequent experiment has recorded 0. Grand unified theories predicted monopolies should have been produced in enormous numbers in the early universe. So Alan Guth proposed cosmic inflation, partly to explain why we don't see them. Inflation dilutes them beyond detection. But then, the Modal detector at CERN's Large Hadron Collider has searched since 2010. Nothing. The Ice Cube Array at the South Pole has scanned cosmic rays for monopole signatures. Nothing. The Cabrera event has never repeated in more than 40 years of continuous monitoring. Every proposed answer either predicts too many or explains why we should never find any. Never why we found one, exactly once. Every compass needle you have ever held obeys equations that are, on paper, incomplete. The magnet on your refrigerator is a symptom of a symmetry the universe seems to have decided against, for reasons no experiment has clarified. Was Cabrera's signal on Valentine's Day 1982 a real particle, a cosmic accident, or the only monopole we will ever see? The next glitch needs no missing particle, only a field you cannot detect. Number 9. The Aharonov-Bohm Effect. In 1959, Yakir Aharonov, a graduate student at Bristol University, and his supervisor David Bohm were working on a routine quantum mechanics problem. They wanted to understand whether the electromagnetic potential, the mathematical scaffolding physicists use to compute fields, was a real physical entity or merely a calculational trick. This was considered a pedagogical exercise. Not a discovery. Classical physics is unambiguous on this point. A charged particle only feels a force when it passes through a region where the electric or magnetic field is non-zero. Outside that region, there is no force. No effect, no influence. This has been the textbook rule since Faraday. Aharonov and Bohm calculated what should happen when an electron passes around, not through a perfectly shielded solenoid. Every field outside is 0. Every classical prediction says nothing should happen. Their equations predicted the electron's wave function would shift anyway. The paper, Significance of Electromagnetic Potentials in the Quantum Theory, appeared in the Physical Review, Volume 115, in 1959. In 1960, Robert Chambers at Bristol produced the first experimental confirmation. In 1986, Akira Tonomura and his team at Hitachi in Japan published a definitive demonstration in Physical Review Letters using electron holography around a superconducting toroid. The shift matched Aharonov's prediction exactly. Physicists initially argued Chambers' setup leaked stray magnetic field. Tonomura's superconductively shielded toroid eliminated that possibility. Others proposed the wave function was somehow sampling the field non-locally in a classical way, but no classical mechanism reproduces the interference pattern. Some tried reformulating the theory entirely in terms of fields rather than potentials. The mathematics either failed or reintroduced the same non-locality under a different name. The effect is now confirmed by dozens of independent experiments across 5 continents. Reality at the quantum level is not built out of the forces you can measure. It is built out of a mathematical object your body cannot detect, and that object is quietly steering every electron and every atom you are made of. If the potential is real, and it fills every region of empty space, what else is it doing that we have not yet noticed? The next one is not theoretical. People have seen it. Physics still cannot name it. Number 8. Ball lightning. In July 2012, a group of Chinese atmospheric scientists, led by Ping Yuan at Northwest Normal University in Lanzhou, were on a routine field expedition. Their equipment was pointed at ordinary cloud to ground lightning strikes on the Qinghai Plateau. They were not hunting anomalies, they were calibrating spectrometers. A regular lightning strike is understood down to the microsecond. Air ionizes, current flows for milliseconds, the channel dissipates. Nothing floats. Nothing lingers. Nothing rolls across the ground for 10 seconds afterward. This is the accepted picture. One of their high-speed cameras captured a luminous, roughly spherical object about the size of a soccer ball drifting horizontally near the strike point for about 1.6 seconds. The spectrometer captured its emission lines. The results were published by Jianyong Chen, Ping Yuan, and Simin Shui in Physical Review Letters, Volume 112, in January 2014. The emission spectrum showed silicon, iron, and calcium, elements consistent with vaporized soil. This is the only known scientific instrument recording of ball lightning under natural conditions in history. Every other account is eyewitness testimony, some dating back to the 1600s. John Abrahamson at the University of Canterbury in New Zealand proposed in a 2000 Nature paper that ball lightning is a slowly burning aerosol of silicon nanoparticles vaporized from the ground. The SEN spectrum partially supports this, but it does not explain why ball lightning has been reliably reported passing through closed glass windows without breaking them. Piotr Kapitsa proposed in 1955 that it was a microwave standing wave, but ball lightning appears in open sky where no cavity exists. Others have proposed slow nuclear reactions, antimatter grains, plasma vortex rings, even hallucination induced by magnetic fields on the temporal lobe. Every model fits one class of reports and contradicts another. There is a phenomenon that has appeared in kitchens and cockpits and Napoleonic battlefields that has electrocuted people in their own homes and standard atmospheric physics. The same physics predicting your weather forecast tomorrow has no confirmed model for what it is. What else has physics been quietly filing under anecdotal for 300 years because the alternative is admitting it does not know? The next one is the field wrapped around this planet, and it is not stable. Number 7. Earth's magnetic field reversals. In 1906, French geophysicist Bernard Bruns was studying volcanic lava flows in the massive central region of France. He was measuring how iron-bearing minerals in cooled lava had aligned with Earth's magnetic field at the moment of cooling, routine work for a paleomagnetist of his era. He expected every flow to point north. The magnetic field surrounding Earth is generated by convection currents in the liquid outer core. That field is what makes compasses work. It deflects the solar wind. It shields the atmosphere from being stripped away. Textbook geology assumes it has always pointed roughly, the way it does now. Brun has found lava that pointed the opposite direction. The rocks were magnetized backwards. In 1929, Motonori Matuyama at Kyoto Imperial University confirmed the effect across dozens of Japanese basalt samples. The most recent full reversal, now called the Brunhes-Matuyama reversal, occurred approximately 780,000 years ago. In February 2021, a team led by Alan Cooper published in the journal Science Evidence that a partial reversal, the Lashchamp excursion 42,000 years ago, coincided with severe environmental disruption and possibly the extinction of Australian megafauna. Geophysicists' proposed reversals are periodic and predictable. The paleomagnetic record shows they are not. Some occur 40,000 years apart, others tens of millions of years apart. Others propose they are triggered by asteroid impacts. There is no consistent correlation. Others propose they take tens of thousands of years to complete. In 2014, an Italian team led by Leonardo Sagnati published lake sediment evidence in Geophysical Journal International that at least one reversal completed in under 100 years. No current geodynamo model reproduces both the irregular intervals and the occasional rapid transitions. Earth's magnetic North Pole is currently drifting from Canada towards Siberia at over 55 kilometers per year, the fastest rate ever measured. The field intensity has weakened roughly 9% since global measurements began in the 1830s. Every satellite in orbit and every power grid on the ground assumes tomorrow will look like today. If the reversal that killed the Australian megafauna is beginning again, what warning does the planet get? The next one hides inside a coil of chilled metal nobody can currently justify. Number 6. High temperature superconductivity. In 1986, Carl Alex Miller and Johannes Jorgbed Noers at the IBM Research Laboratory in Zurich were investigating ceramic oxides. Ceramics are famously insulators. They break. They shatter. Nobody serious expected them to conduct electricity at all, let alone with zero resistance. Miller and Bednorz were following a hunch nobody funded generously. Superconductivity, the flow of electricity with zero resistance, had been explained in 1957 by John Bardeen, Leon Cooper, and Robert Schrieffer at the University of Illinois. Their BC's theory predicted a hard ceiling. Above about 30 Kelvin, roughly minus 243 degrees Celsius, phonon-mediated electron pairing should break down. Superconductivity above that should be impossible. Their lanthanum barium copper oxide sample became superconducting at 35 Kelvin. Above the BC's ceiling, it should not have worked. The result appeared in Zeitschrift for Physik B, volume 64, in 1986. Within a year, Paul Chu at the University of Houston and Ma Quen-Wu at the University of Alabama in Huntsville pushed the transition temperature to 93 Kelvin using yttrium barium copper oxide above the boiling point of liquid nitrogen. Miller and Bednorz received the Nobel Prize in Physics in 1987, less than a year after publication. 40 years later, materials have been found that superconduct above 200 Kelvin under pressure. The theory to explain any of them does not exist. Physicists proposed extensions of BCEs with stronger phonon coupling. The numbers do not fit. They proposed spin fluctuations as the pairing mechanism. This works for some cuprates and fails for others. Philip Anderson's resonating valence bond theory has partial success and partial failure. Iron-based superconductors, discovered in 2008 by Hideo Hosono at the Tokyo Institute of Technology, obey different rules again. Every proposed unifying framework has died in a specific experimental result. Every Murray machine that has ever imaged a human brain relies on superconducting magnets. The engineers who built them do not know, at the deepest level, why the wire in the magnet works. If the physics we use is not the physics that is actually happening, what happens when we try to push it further? The next one is a natural object so violent that atomic physics stops working near it. Number 5. Magnetar field strengths. In the late 1980s, Robert Duncan and Christopher Thompson at Princeton were trying to explain a class of astrophysical bursts that ordinary neutron star models could not account for. They were not proposing a new object. They were troubleshooting a data problem. They wanted the standard picture to hold. A neutron star is already an extreme object, the compressed core of a dead massive star. Roughly the mass of the Sun packed into a sphere about 20 kilometers across, with a magnetic field about 1 trillion times stronger than Earth's. This was, until the 1990s, the ceiling. Nothing was supposed to be stronger. Duncan and Thompson calculated that a small subset of neutron stars born from rapidly rotating collapsing cores could generate magnetic fields 1,000 times stronger still. The paper appeared in the Astrophysical Journal Letters in 1992. The name they coined was Magnetar. A confirmed magnetar has a surface field of roughly 10 to the 15 Gauss, 100 trillion times stronger than a refrigerator magnet. On December 27, 2004, a giant flare from the magnetar SGR 1806-20, approximately 50,000 light-years away, briefly ionized Earth's upper atmosphere and saturated satellite detectors across the solar system. Astronomers first proposed magnetar bursts were ordinary neutron star glitches. The energies were wrong by orders of magnitude. Others proposed accretion from a companion star. Magnetars are isolated. Others proposed conventional relativistic jets. The spectrum did not fit. The Duncan-Thompson model is the only surviving explanation, and it forces something unsettling. At a magnetar's surface, atoms would deform into thin cylindrical shapes because the magnetic force on the electron exceeds the atom's own electrical binding. Chemistry, as we know it, cannot exist there. A magnetar could, from a distance of 1,000 kilometers. Disassemble the biochemistry of every cell in your body by unpicking the electron orbitals that make molecules possible. Not through radiation, through the field alone. The Milky Way contains roughly 30 known magnetars. There are estimated to be millions more, silent, undetected. Where are they? The next one is not out in the galaxy. It surrounds you right now. Number 4. The electromagnetic dark matter search. In the 1970s, American astronomer Vera Rubin at the Carnegie Institution of Washington was measuring how fast stars orbit the centers of spiral galaxies. She expected the outer stars to move slowly, as planets in our solar system do. She was performing catalog-grade observation. This was not supposed to overturn cosmology. If a galaxy contains only the matter we can see, Newton's laws, the same laws that put spacecraft on Mars, require outer stars to orbit slower than inner ones. This is held for every gravitationally bound system ever tested. Rubin found that outer stars orbit at roughly the same speed as inner ones. The galaxies should be flying apart. They are not. Her measurements, published throughout the 1970s in the Astrophysical Journal with Kent Ford, forced the conclusion that roughly 85% of the mass in every galaxy is invisible. Roughly 27% of the total energy content of the universe. In June 2020, the Exanon 1T experiment at Gran Sasso National Laboratory in Italy reported an unexplained excess of electronic recoil events, briefly interpreted as possible dark matter. In July 2022, the follow-up Xenon experiment confirmed the excess had been a tritium contamination. Every subsequent direct detection experiment, LZ in South Dakota, Panda X4T in China, has returned nothing. Physicists proposed YMs, weakly interacting massive particles. Every mass and cross-section window has now been ruled out. They proposed axions. Searches by the AtomX experiment continue with no confirmed signal. They proposed modified Newtonian dynamics, removing dark matter entirely. The bullet cluster collision, imaged by Douglas Clue's team in 2006, showed gravitational lensing offset from the visible gas. Dark matter behaves like matter, not like a modified law. Sterile neutrinos, primordial black holes, dark photons, each proposal has either been excluded or evaded detection for decades. Right now, as you read this, roughly 1 billion dark matter particles are passing through your body every second. They carry more of the universe's substance than everything you have ever touched. You cannot feel them. Nothing you own can detect them. If dark matter refuses to interact with light after 50 years of searching, is it matter at all? The next glitch is subtler, the one thing physics thought was settled. Number 3. Photon mass upper limits. In 1936, Alexandru Proca in France was writing down equations for a hypothetical massive photon. This was not a serious challenge to Maxwell. It was a mathematical exercise, a way of asking what electromagnetism would look like if the assumption of massless light were relaxed. Proca had no reason to think he was describing reality. In every physics textbook, the photon is exactly massless. This is why light travels at exactly c. Why the electromagnetic force has infinite range. Why Coulomb's law falls off as 1 over r squared and not faster. These are foundational. They are load-bearing. No experiment has ever proven the photon's mass to be 0. Every experiment has only ever placed an upper limit on it. The limit gets smaller. It never reaches 0. The current upper limit from the particle data group is roughly 10 to the minus 18 electron volts, based on solar wind analysis by Dmitry Ryutov at Lawrence Livermore, and ray derivations by Alfred Goldaber and Michael Nieto in a landmark Reviews of Modern Physics paper in 2010. In 2003, Jun Luo and colleagues at Huazhong University in Wuhan used a torsion balance to constrain the mass further. Publishing in Physical Review Letters, every measurement is a ceiling, not a floor. Theorists argued the photon must be exactly massless for gauge invariance. Introducing a mass via the Stuckelberg or Higgs mechanism, in principle, does not have to break the underlying symmetry. The argument became aesthetic, not logical. Others argued cosmological observations would detect any mass through dispersion of light from distant sources. They constrain, they do not exclude. Others invoked analogies to the third law of thermodynamics. You can approach zero, but never reach it. No one has produced an experiment whose null result would be conceptually impossible for a non-zero mass. If the photon has even the smallest mass, Coulomb's law is wrong at very large distances. Every galactic magnetic field measurement, every deep space communication sits on an assumption physics has never actually verified. What is the difference between exactly zero and smaller than we can measure? The next one takes empty space and shows it is not empty. Number 2. Vacuum birefringence. In 1936, Werner Heisenberg and his student Hans Euler at the University of Leipzig were exploring the consequences of Paul Dirac's electron theory. They were attempting to understand how the sea of virtual particles predicted by quantum electrodynamics would respond to extremely strong external fields. Their calculation was purely formal. Nobody expected it to be testable. Empty space, in classical physics, does nothing. Light travels through it in straight lines with fixed polarization. No medium. No interaction. Two beams of light cross without disturbing each other. This is why astronomers can see galaxies billions of light years away without distortion. Heisenberg and Euler predicted that if the magnetic field became strong enough, around 10 to the 9 Tesla, the vacuum itself would behave like a birefringent crystal. Light polarized along the field would travel at a very slightly different speed than light polarized across it. The result appeared in Zeitschrift for Physik, volume 98, in 1936. On Earth, no laboratory can produce fields anywhere near that strength. In 2016, Roberto Mignani of the National Institute for Astrophysics in Milan led a team that used the European Very Large Telescope in Chile to measure polarized light from the isolated neutron star RxJ 1856.53754. Their paper in the Monthly Notices of the Royal Astronomical Society, volume 465, reported the first optical signature consistent with vacuum birefringence. At roughly 4 sigma significance. The Pivlas experiment in Italy has been trying to detect it in the laboratory since 1992 and has not yet succeeded. Skeptics propose the polarization was intrinsic to the star's own atmosphere. Detailed modeling by Ilaria Chiazzo and colleagues ruled out atmospheric explanations. Others proposed instrumental polarization from the telescope. Careful calibration excluded it. Others proposed magnetized dust along the line of sight. The line of sight is unusually clean. A 4 sigma detection is not a discovery. Confirmation requires an X-ray polarimeter capable of measuring the effect more directly. A NASA-led mission called IXPE, launched in 2021, and is still building statistics. The vacuum around you is not a void. It is a medium, a foaming virtual quantum medium that only reveals itself under conditions your body cannot survive to observe. If empty space bends light, what else does it do that we are simply too weak to force it to show us? And finally, the closer, the most confirmed glitch of them all, and nobody agrees what it means. Number 1. The Casimir effect. In 1948, Dutch physicist Hendrik Casimir at Philips Research in the Netherlands was trying to solve an industrial problem. He was studying colloidal suspensions, how tiny particles remain suspended in fluid, for a paint and pigment application. His conversation with Niels Bohr redirected him toward a stranger question. What does the quantum vacuum actually do between 2 parallel plates? Empty space, in classical electromagnetism, contains no energy and applies no force. Two uncharged, non-magnetic mirrors sitting parallel in a perfect vacuum should feel no attraction to one another. This is common sense. Casimir calculated that the plates would attract, not because of charge, not because of gravity, because empty space itself, filled with virtual photons of every wavelength, has fewer allowed modes between the plates than outside them. The imbalance pushes. The paper appeared in the Proceedings of the Royal Netherlands Academy of Arts and Sciences, Volume 51, in 1948. In 1997, Steve Lamoureux at the University of Washington measured the force to within 5% of Casimir's prediction, publishing in Physical Review Letters. In 1998, Umar Mohideen at UC Riverside confirmed it independently with an atomic force microscope. The effect is now a real design constraint in microelectromechanical systems, where the plates are so small the vacuum pressure can stick them shut. Physicists have detailed technical descriptions of the Casimir force. They have engineering formulas. What they do not have is agreement on why the vacuum has this energy in the first place. Quantum field theory predicts a vacuum energy density roughly 10 to the 120 times larger than what cosmology observes. This mismatch, the cosmological constant problem, is the largest quantitative failure in the history of physics. The force is real. The framework predicting it is off by 120 orders of magnitude in a closely related prediction. The chair you are sitting in is separated from you by short-range forces that are, at bottom, negotiations with a vacuum whose energy content physics cannot correctly compute. If the theory that predicts this measurable force is wrong by the largest margin of any prediction ever made, what exactly are we measuring? Every glitch on this list, the monopole that should exist and does not, the field you cannot feel that steers electrons, the vacuum that pushes back, sits at the center of the theories physicists trust most. This is not the edge of knowledge failing. This is its interior, quietly refusing to close. The universe is not confused. We are. If you want to see more videos like this, click the video on screen now.